Okay, we're back at it, and now we're looking at example D. And just like in the previous video, I am required to take a look at this example problem, figure out how many different signals I actually have from the compound, and then rank those signals once I determine that. So again, it's all about baby steps. We started off basic foundation of number of chemical shifts, and now we've built up on top of that by ranking those chemical shifts amongst each other. So let's take a look at D. So I need to figure out how many chemical shifts. Before I rank them, I'm going to have to figure out how many I have, right? Okay, so here I'm going to quickly look at this O, because that lets me know, hey, this is electronegative. I know that a lot of what we need to do is around that electronegative atom, so I might as well start there first. And then here on the right-hand side, I see a CH3 group, and that CH3 group has hydrogens associated with it. So guess what? Ding dong, I'm going to get a signal there. All right, on the other side of that oxygen, I see a carbon that has one hydrogen. So guess what? Ding dong, I'm going to see a different shift that's going to happen there as well, because they're different from each other. Now I'm just going to move left-handed because I'm a left-handed person. That's right, I'm sinister in the world of organic chemistry. So if I go to the left-hand side, this is a CH2 group. That's different than a CH. That's different than a CH3. So, ding dong, I'm going to get it there. But, guess what? If I go right-handed, I see another CH2 group. Are they the same? Well, that CH2 has a CH with an O on the left and a CH3 on the other side. And then if I look at this one, that CH2 group has a CHO on one side and a CH3 on the other. So that makes my job easy, because this particular carbon and that particular carbon is equivalent because they have equivalent protons. All right, so that means I don't ding-dong the other side. It's an equivalent signal from what I've already labeled. All right, now next is this CH3 group, and of course, ding dong, that is going to be different. That's a CH2, that's a CH. This is a CH3 group, but that's on an oxygen, and this one is not on an oxygen. So that means it is not equivalent, it is different. So what I'm going to see in D, I'm going to have to label an A, B, C, and D, because there are 4 different signals that are associated here. Now, if I look on the other end of the molecule, the reason that I didn't ding-dong the right-hand one is because that's also equivalent. So that CH3 group is on a CH2 on a CH. This CH3 is on a CH2 on a CH. It is a symmetrical molecule from the middle. So everything to the left is identical to everything on the right. Okay? So 4 signals in total, and now we need to rank them. Just like before, I look at my electronegative atom, and that's this oxygen, and that oxygen is going to suck electrons away. So that is going to suck electrons away from that particular carbon with those 3 hydrogens, as well as that particular carbon with that 1 hydrogen. So if I need to rank one of these as being the most pulled, or the most positive, or the unshielded one out of the bunch, which one I'm going to pick? Well, we kind of done this in B already. It's going to be the carbon with that 1 hydrogen. And that's because carbon is the bully too. And carbon's going to come in and say, give me your nickel. And then hydrogen's going to go, okay, here's my nickel. Now go away and leave me alone. There's no friends to take up for me. I'm just so lonely in the world. So that carbon is going to be the least, or the hydrogen will be the least shielded that's on that particular carbon. All right. Now, if I look, and I need to stay away from the bullies, right? That's the smart thing to do. So which one is going to be the furthest away from the bully? Well, here's my electronegative bully, the oxygen, and the CH2 group is near it, and the CH3 group is a little further away from it. So that means that the CH3 group on either end, either to the left or to the right, because they're equivalent, that particular CH3 group is going to be the most shielded out of the bunch. Again, What does that mean? That means that it has more electron density around those hydrogens. That electron density is not getting pulled through the molecule by the electronegative oxygen. You see what I'm doing? I'm slowly weaving in real terms, real sciencey terms, versus bullies and lunchrooms and nickels for, probably the paper milk carton back in the day. So because this is the most shielded with electron density, that means that this is not going to be exposed very strongly to the magnetic field, which means it doesn't take a lot in order to get this to flip and produce a signal on its way back down to ground state. So this CH3 group, well, folks, that's going to be my A mark. But I'm also going to have to put an A over here because those two are equivalent to each other. Right? Now, the next one, the one that's furthest away, would be the CH2 groups on either side of that middle CH group. So this will be it will be next, and that will be the B choice. And now this oxygen that has flanked on each side a carbon and a carbon, I need to compare those two to each other. And we've already said the CH is the least shielded, which means the carbon picks on that one hydrogen, pulls the electron density away from that one hydrogen, and that hydrogen is more positive than on the other side of the oxygen. It's got 3. So for that particular case, hydrogen says, I brought my buddies today. You're not going to take my lunch money. So that carbon is going to come next. So this will be C. And then finally, D will be here in the middle. So if I go back up to the top right-hand side where we did this little schematic of an NMR, the A hydrogens will be closest to the TMS 0 mark. The B will be a little bit further away. The C will be a little bit further away from that. And then finally, the D will be the furthest in that particular compound. It is the most exposed. It is the most positive out of the bunch. It relates and aligns itself with the magnetic field, the strongest out of all the choices. And because of that, it takes more frequency in order to get it to flip. Okay? Now, let's take a look at E, which is down below, not to the side. They kind of pulled a trick on us here. Okay, so for E, again, I'm going to look at electronegativity, and that electronegativity is kind of happening right in here. So I need to take a look and just determine the number of different types of signals first. So I'm going to ding-dong that hydrogen, because there's 3 of them on that carbon, and then ding-dong that hydrogen, because there's 2 of them near a carbonyl. This one's a little further away, so it's different. Even though it's a CH2, it's not directly connected to a C double bond O. So ding-dong, that one, and ding-dong, that one. So we're going to get 4 different signals here. Once again, I'm going to probably see an A, B, C, and D. Now it's just an order of how do we rank these things, right? So I need to look at the one that's probably the most shielded. That would be the easiest, and the least shielded. Those are always the extremities, and it seems like those are always the ones that we can kind of rely on first. So I take a look at the electronegative area, which is going to be right in here, the C double bond O and O group. That's where the electronegativity lies. And if I had to pick out a point in the molecule that's the furthest away from those bullies, I'm, of course, probably going to pick out these protons on that particular carbon. So these are the most shielded out of everything. And because of that, this is going to get A in this example problem. They're the most shielded. The magnetic field, it's not going to align very strongly with it. It doesn't take a lot of energy to get them to flip, and it's going to be very low on the frequency side. In other words, it's closest to the 0 mark, like all the other examples that we talked about. So next in line would be this CH2 group, right? I'm getting closer and closer to that electronegative area. So this is probably going to be B. And now we're going to take a minute and we're going to pause and we're going to think about this. Do not rush these problems, right? You really want to analytically think these out. So I've got a carbon to the left of the carbonyl and a carbon to the right of that oxygen. And I need to figure out, okay, well, which one of these would actually be next in line? Which one of these would be the C one? And you might look at this and make the wrong judgment call if you're not careful. So again, I want you to think about electron pullers. What are the major electron pullers here? Well, it's the oxygen. Oxygen is highly electronegative compared to those protons. So what you actually need to rank here is the oxygen that is directly connected to that carbon with those 3 hydrogens, and then the oxygen that is on a carbon that then on another carbon that then has the 2 hydrogens. Do you see where I'm going with this? I hope so. So that electron puller is connected to a middle man or middle woman, and that is a carbon in that spot before it even gets to that carbon with the 2 hydrogens. And it's all about the protons here, right? That's what we're focused on. So what this means is that CH2 group will be the C. That will be the next in line. And then the CH3 group here on the end to the right is going to be our D. That will be the most unshielded out of the bunch. And that will be the most positive out of the bunch. Even though it has 3 hydrogens, doesn't matter, because that oxygen is a bigger bully than carbon will ever be. And that oxygen is directly connected to that carbon that has those protons. On the other side, not so much. That oxygen's got to go through a carbon before it gets to the carbon that has the protons on it. So that's a little bit different story. So just because of the way it's connected, that carbon that's directly connected to the electronegative atom, that is going to be D. All right. So maybe that would have tricked you if you weren't careful. All right, next up is F. So I'm going to ding-dong you to death, I think. So if we take a look at F, here is the electronegative atom. I just really like to kind of start there. I think it gives me a good starting place for all of this mess. And it looks like I'm going to ding-dong, and then ding-dong, and then ding-dong there. And then on the other side, I have a CH group that really hasn't shown up yet. So ding-dong there. And then off of that one, I see a CH3 group, which is different than that CH. And that CH3 group is also different than the first CH3 group that we did over here to the left. And that's because this CH3 is connected to a CH. And that CH3 group to the left is connected to a CH2, not a CH. So ding dong, going to be that one. Now, the good news is that I don't have to ding dong no more. And that's because this methyl group that's pointed down is actually equivalent to the methyl group that I have already ding-donged here on the right-hand side. So these two are going to be equivalent to each other, right? Both CH3 groups are connected to a carbon with a hydrogen, and beside of that is an oxygen. So it doesn't really matter which one it was. Again, take a hydrogen away, put a bromine on it. Name it. You're going to get the same name no matter which hydrogen that you picked and erased and put a bromine there. So because of that, they are equivalent hydrogens to each other. All right, so now that we ding-donged, now that we know how many signals that we have, 1, 2, 3, 4, and 5, it looks like I'm going to have to do an A, a B, a C, a D, and an E. All right. So just like before, I like to start with the one that's furthest away from the bully. I mean, that seems like that's the easiest path of resistance, I guess. And once I start there, that will give me a guide on where to go from that point. So the electronegative bully is there. It's the oxygen. So let's look at which one is the furthest away. So if I go left-handed, 1 carbon, 2 carbon, 3 carbon, this one is going to be the most shielded because it's the furthest away from that electronegative atom. So that means that CH3 group is going to be our A signal, closest to the TMS of 0 mark. Most upfield from everything else. Now, as I get closer in to the oxygen, then I'm going to start playing around with the exposure to the protons and how they start interacting with the NMR magnet. All right, so what comes next? Well, we're going to move 1 carbon in, right? So for instance, here's my electronegative oxygen, and this one is 1 away, 2 away. And then this oxygen, we've got 1 away, 2 away. So according to carbon length, each one of these are about the same distance away from that oxygen, right? So now, before you go and rush into a decision that you're going to definitely regret later, analytically think. To the left, I have a CH2 that's 2 carbons away, and to the right, I have a CH3 that's 2 carbons away. They're both the same distance away from the oxygen. The difference is how many protons that they have. And remember what I said. Hydrogen brings buddies. So, with this particular carbon, yeah, it's electronegative too. There's no question in that. It is electronegative. Not huge, but it's electronegative. And this carbon has to punch 3 hydrogens. Those hydrogens all have buddies at the lunch table. Though that carbon is not going to get that much lunch money away from those protons. And because of that, that one is going to be shielded. Now, on the other side, 2 carbons away, I've got this carbon that only has 2 hydrogens there. So at the lunchroom, that hydrogen does have a buddy, and that carbon can punch, and get lunch money, and it can get it a little bit easier. So that means these hydrogens are more broke. More lunch money has been taken away from them. They are more exposed to the fun and the humiliation that everybody else is going to give them in the class because they got beat up at lunch by this bully that's carbon who's weak anyway. So that means that out of those 2 choices, the CH3 would actually be the next in line. And guess what? These 2 things are equivalent, so I'm going to put B's on both of those because they're the same. And then C will come here because that would be the next in line. All right, so now what I've got left over are 2 more signals, one to the left and one to the right. The signal to the left is 1 carbon away. The signal to the right is 1 carbon away. So I can't really use that judgment call to go by. And just like before, I'm going to have to use the number of hydrogens on this thing to determine which one would come next. So this carbon has 2 hydrogens to fight, and this carbon only has 1 hydrogen to fight. So because of that, this CH group, that carbon's going to beat the hydrogen up and take its money, and that oxygen's going to do it as well. It can do it a little bit better here. So this hydrogen that's on that particular carbon will be the least shielded out of the bunch, and this one would be next in line. So that means the D would come from those protons, and the E will come from that 1 proton beside of the oxygen. That E proton is the most deshielded out of the bunch. The electron cloud is very low, and that exposes the proton to the magnet of the NMR more so, which means more frequencies required in order to get that to flip and off the swing set. All right? Now, let's take a look at G. Very similar to some of the things that we've done already, right? I mean, it looks very similar to E here. The difference is that the oxygen's not involved. So just like before, ding dong, ding dong, ding dong, ding dong. I'm going to get 4 signals that come from this example problem. They're all 4 different. And this is the electronegative atom that's going to be present in the molecule. And then for G, the furthest away from that electronegative atom, well, the most shielded that it's going to be, right? So it looks like that's the CH3 group over here. So this is going to be the A signal that I want to label, closest to the TMS, lowest frequency in order to get it to flip, based on how this example problem was worded. The next one, well, okay, that would be this one, of course. It's further away than that carbon and that carbon is to that oxygen. And then I get to a point where this carbon is a carbon away and the carbon to the right is 1 carbon away. So as far as distance goes, these are the same distance here. So I can't really look at distance anymore. I have to look at the number of hydrogens on these carbons. So what I would see is that this carbon has 3 hydrogens that it has to fight against. The electron cloud would be more on this side than that side because carbon can't put up a fight with 3 hydrogens as well as it can with 2. So that means that this CH3 group on this side would be the next in line. This will be the C, and this will be our D mark. So the CH2 that's located to the left, those hydrogens will be the most exposed. The carbon can pull them away a little bit more. The oxygen can pull them away a little bit more. And they're more exposed, meaning they're more positive, meaning they align stronger with the field, meaning it takes more energy to get them to flip. And all right, H. We're almost done. Almost done. But again, what do I always say? Practice makes perfect. So we've got 2 more examples before we're perfect, right? All right, so for H, let's ding-dong it. Ding dong, ding dong, ding dong, ding dong. I see 4 signals here. And the reason that there's 4 is because this CH3 group is on that CH, nothing on the other side. This CH3 group is on the CH with nothing on the other side. They are equivalent. So I know that I'm going to get 4 signals, which means in this example problem, I'm going to have an A, a B, a C, and a D. I'm just going to rank them. So just like before, I go to the most electronegative atom in here, and that is the oxygen. That's where the electronegativity is going to take place. The furthest one away is going to be the most shielded, right? It will have more electron density around those protons, and it's not going to align itself very strongly with the magnetic field because of that. These electrons are kind of negating that positive charge out. So that means that the atoms that are furthest away from the electronegativity ones, or the electronegative ones, this is going to be A. That is equivalent, so that also is an A. Take care of both of those at one time. Next in line, what would it be? So here's this oxygen group, and then there's a carbon to the left, there's a carbon to the right. But this one is furthest away versus those 2. So that means that this one is going to be B. That will come next in line in the NMR. We're working ourselves more and more downfield. And then the oxygen will have one to the left and one to the right. So now position-wise, we're pretty good. They're kind of equal. So what's going to determine the factor now is the number of protons that are on the carbon. So this carbon has 3 to fight against. This carbon only has 2 to fight against. It can take more lunch money away from that hydrogen 2 set than it can take away from the 3 set hydrogen. So that means C is going to be here on the end. And then D will be more nestled on the inside. So D is the most deshielded out of the bunch. That means the carbon will pull more lunch money away from the hydrogens, and that oxygen will help and aid in that pulling away, and those hydrogens are more exposed. They're more positive. They align themselves with the magnetic field stronger, and it takes more energy to get them to flip. Again, I keep saying that over and over and over because it helps you understand what exactly NMR is actually doing. We never want to forget that, right? All right, so let's take a look at example I, and that's our last one. Finally! So with this example, we need to ding-dong the molecule. So here's the electronegative atom, chlorine, and then on that, we're going to see a CH, ding-dong, and then beside of that is a CH3, ding-dong, and then beside of that is another CH. Well, is that CH different than that CH? Well, yeah, it is. It's different because this CH is on a methyl and a chlorine, and this CH is on a methyl, but no chlorine here. So ding dong, we're going to get a signal there. And now we're going to look at the last methyl group, and you need to say, okay, well, is this methyl group different than the other methyl group that we did? This CH3 group is on a CH with another methyl. This CH3 group is on a CH with no other methyl. So yes, ding dong, they're going to be different. Now, the good news is that this methyl group and this methyl group, they are equivalent to each other. So I only have an A, B, C, and D that I need to worry about because that methyl is on a CH and this methyl is on the same CH. There's no other neighbors on the other side. So these things are equivalent to each other. So I'm going to get 4 signals here, and now we need to rank them. So the electronegative atom is this chlorine, and the furthest away we can get from this thing, the better off we're going to be. No bullies. So the furthest away that we can get is basically going to be the methyl groups that are equivalent to each other. So these are going to be the A's. They're the furthest away. So as far as the signal goes, they will flip first, right? Charge is not exposed. It takes very weak magnet to kind of align them up and to get them to flip and produce a signal because of that. The electron density cloud is there to kind of help cover up that positive charge. This is the furthest away. That's the first signal that we're going to see. All right, so what's next in line? Well, here is the carbon, and one to the left and one to the right. All right. So the one to the left has 1 hydrogen on it. The one to the right has 3 hydrogens on it. That carbon can't beat up the hydrogens and take as much lunch money as this carbon that only has 1 hydrogen to deal with, right? It has a much better, easier time handling that 1 hydrogen than 3. So that means that this will come next, and that will be our B signal. And that means that this will come next, and that will be our C signal. And then finally, the hydrogen on the carbon directly connected to the halogen. That is our D signal. That proton is the most deshielded out of the bunch, meaning the carbon's going to be an electron puller. That chlorine is also going to be the electron puller. That hydrogen is more exposed. The hydrogen is more positive because of that. That hydrogen aligns stronger with the magnetic field because it's more positive, and that hydrogen requires more frequency in order to get it to flip because it aligns itself with the magnetic field a little stronger. So that's the furthest away from the 0 mark, and that would be the furthest away in the what we would call downfield region of the NMR. All right, so there's our example problems. Quick review of determining the number of signals, but an additional step of being able to rank them. All right. Okay, so in the next video, we're going to start looking at characteristic properties that functional groups bring to the table. Now that we have this idea that different groups are going to show up differently on the NMR based on what's around them and based on what their neighbors are, this is going to give us a grasp on what these characteristic kind of signals and where they're located show up. And that will become clear in the next video when we start it. So here is where I'll stop. Might be a good breaking point for you as well. And then just come back whenever you're ready. We'll pick up with these characteristic signals that we'll see in NMR, and we'll relate that to kind of what we've already been doing. So that way we can start connecting more of the dots of nuclear magnetic resonance.